Okay, hi. This is my video number 15, where I'll give you some example on what we have discussed thus far on the volterra integral equation. Yeah. So lecture number 15, I will talk on the example. Just I'll focus on the example on this video. Let's first consider on how to get the resolvent kernel. Yeah, find the resolvent kernel. Find a resolvent kernel for a volterra integral equation, for non-homogeneous volterra integral equation, where the kernel is given with kernel as follows. So first we have k xt is ex minus t, and second we have kxt equal to 1, and third we have kxt is equal to 2 plus cos x over 2 plus cot t. Alright, so this kernel is kernel to the non-homogeneous integral equation, meaning that our a non-homogeneous volterra integral equation is given as ux is equal to, we have fx plus, so integrate from some number a to x, we have k is given here, so we have ex minus t ft dt. Okay, so this kind of volterra integral equation, now we are going to find the resolvent kernel r k t lambda. So that's what we're going to find. Okay, so I'll do the first one, the second one and third one you do this as an exercise. Yeah, so for the first one, so we have the iterated kernel. K1 is, let me write the iterated kernel. We have K1 is xt is kxt, which is given as ex minus t. Okay, this is solution for number 1. And we have K2 or km xt is given as integrate from t to x k xz km minus 1 zt dt. So it is z, should be dz now. Okay, so from here we can find what k2 is. Let's do this. K2 xt is integrate t to x. Okay, so we have kxz, k1, kxz, k1 zt dz. So what is this? This is integrate t to x, k kxz, so t we change, so ex minus z, so we have ex minus z. And for k1zt, here, this is k1x, so k1zt, so we have x replaced with z, so ez minus t dz. So you can see here z cancel out, so what left is z x minus t. I put the outside, and then t to x dz. So this part here, that give you x minus t. So your solution should be x minus t x dollar x minus t. Alright, And then we can find there's K2, we can find K3. Let's see, we can find K3. So K3 using this formula there. So K3 xt is integrate t to x kxz k2zt dz. Okay, general formula is like that. So integrate from t to x, kxz is given here, so we have xz, x minus z, ex minus z, and k2zx is you have here, we change t with x with z, so we have ez minus t, z minus t d dz. So what we have from here, you can take out, this is z cancel out, x minus t, so we have ex minus t, and here we have z minus t dz. So that will give you an we evaluate x z from t to x. Okay, that will give you, because here you got t, or you have z cube and z. Okay, so you have x minus t squared, this is x3 over 2 factorial. Okay, we integrate, just integrate those things as well, so you got those. Okay, and then if you proceed this, we can find x3. Here you have x k1, k2, k3, and so on. You can find up to kn. Yeah, kn xt. This is ex minus t, x minus t. So now you see this is so less 1, right? 3, 2, 2, 1. So we have in n minus 1, and divide by n minus 1 factorial over n minus 1 factorial for all n natural number. 0, 1, 2, 3, 4, 5, and so on. Okay, so having obtained the kernel k1, k2, and so on, we can find the resolvent kernel. Have you obtained that? So the resolvent kernel is given. So therefore, the resolvent kernel, which is we denote as r xt lambda, this is by definition is m from 1 to infinity, lambda m minus 1 km xt. So if you substitute those k that we have obtained here earlier, so this gives you m equal to 1 to infinity lambda m, and km is given as ex minus t, x minus t, m minus 1 over m minus 1 factorial. Okay, just replace with this. This is this one that we obtained in the previous one. Okay, so therefore we can I can factor out this ex ek. So what left is that if you can factor out this ex minus t, okay, plus you're going to have ex minus t, then lambda x minus t over 1 factorial, and plus we have lambda, should be lambda squared e x minus t lambda squared t minus x squared over 2t, and so on. So if we can simplify this, this will give us, this is e x minus t, and from this we have you can factor out this 1 plus lambda x minus t over 1 factorial plus lambda squared lambda minus t x minus t, so x minus t, where is it, lambda squared x minus t here, x minus t squared over 2 factorial, and so on. Okay, so if you do this, this is the geometry series for e lambda x minus t. So therefore we have, this is e x minus 1 plus lambda. So this is the resolving kernel that we are looking for. Okay, if you know f in the equation, if you know f here, if you know f, you know the kernel, then definitely we can solve this problem. Okay, for question number 2, I give you the solution. R xt lambda is given as 1 plus lambda x minus t over 1 factorial plus lambda squared x minus t squared over 2 and plus so on. Okay, this is equal to e lambda x minus 1, and solution number 3 is given as, so hopefully you can read those things. Solution number 3, r xt lambda, this is 2 plus cos alpha over 2 plus cos alpha. Kita bagi nama cantik dulu, put it aside. Okay, this thing, and then inside there we have 1 plus, just factor out everything there. So 1 plus, we have this part there, so lambda x minus 1 x minus t, okay, plus lambda squared x minus t squared, and so on. Okay, and this part here basically is e lambda x minus t. So therefore we have again our problem. Therefore our problem is the solution r x t lambda is equal to 2 plus cos x plus 2 plus cos t and plus some series plus lambda squared x minus t over 2 factorial plus sorry, this should be lambda 1 factorial. Okay, this should be 2 factorial. So t squared 2 factorial and so on. Okay, and in fact inside bracket there, this is just the e lambda x dollar x minus t. So therefore our solution for the example 3 here are xt lambda, this is 2 plus cos x 2 plus cos minus 2 plus cos t e x lambda x minus t. So that's the solution for number 3. Okay, now we have found the resolvent kernel. Now we are going to use the resolvent kernel to solve the appropriate volterra integral equation. Okay, let me give you example. So in the note you can see written as a type 2, yeah. Type 2, just to make a difference from the case one. The first case is that the integral equation depends very much on the tree where we create, or the boundary condition is in tree. Okay. What did I say now? Something wrong. I think I said something, but I forgot this thing. What is it? Yeah. Okay, doesn't mind. Doesn't matter. We just carry on with this. I'm going to solve the volterra integral equation using the using the resolvent kernel. Okay, so basically what we have the volterra integral equation. We have the form of resolvent kernel, and we can write the solution in terms of the resolvent kernel. Yeah. So let's consider this. Consider this integral equation. Yeah. We consider ux is equal to 1 plus x squared plus integrate 0 to x, and we have 1 plus x squared over 1 plus t squared, yeah, t squared ut dt. Okay, let's consider that. Now here we have fx. Our fx is equal to 1 plus x squared. Our fx is 1 plus x squared. Our lambda is equal to 1. We have lambda here. Lambda is 1. And our kxt is given as 1 plus x squared over 1 plus t squared. Okay, this is squared. So what we need to do is that we want to find the general term for the kernel. We need to find the general term for the kernel, because remember that the resolvent kernel is written as r x t lambda. This is summation of lambda m minus 1 k m x t. Okay, so we need to find this km. So to find that, we used iterated kernel. Let me write those iterated kernel. It's okay to write again and again. So we have k1 xt, this is equal to k xt. In this case our k xt is this, alright, that one. And then our km xt is integrate from t to x k xz km minus 1 zt dz. Okay, so we have k1, our k1 is this is 1 plus x squared over 1 plus t squared, that our z, our k1. Then we can find k2. Based on that we can find k2. Our k2 is given as k2 xt. This is integrate t to x k, which is this k xz, change t with z. So we have 1 plus x squared over 1 plus z squared. Okay, and this one is k1, this is k1 again zt. So we change x with z. So we have 1 plus z squared over 1 plus t squared. This is z squared dz. As you can see here, this can cancel out. What left, this is 1 plus x squared, 1 plus t squared, free of z. So we have 1 plus x squared, 1 plus t squared, then integrate dz x to t. So we have x minus t. That's k2. You can find k3 by doing the same. K3 xt is, what is k3 xt? K3 xt is we integrate t to x. Our kxz is that 1 plus x squared over 1 plus z squared. And k2 here, k2 zt. So we have 1 plus z squared over 1 plus t squared. We have z minus t dt. Again, you can cancel out this. So what you have, this, you can take out that and we'll integrate just z. So you got x, this is dz, d squared, z squared over 2 tz, and substitute the value. So you got, okay, so this you got 1 plus x squared, 1 plus t squared, x minus t squared over 2 factorial. So you can see here. So this is k1, this is k2, this is k3. Then basically we can have for k4. Yeah, for k4, this should be 3. Yeah. So if you find k4 just based on that, if you find k4 should have 1 plus x squared over 1 plus t squared, x plus t 3 over 3 factorial. Okay, that's k4. And therefore you can find the km. You just need to add those things. You can find up to km xt. This is 1 plus x squared over 1 plus t squared. We have x minus t m minus 1 over m minus 1 factorial. That in general. Okay, once we obtain those things, you can find the resolvent kernel. So let's write those things. So therefore our resolvent kernel is given as so therefore we have R we have r x dx. Okay, so this is, by definition, this is summation of lambda m minus 1 km xt. Okay, so this is summation for m 1 to infinity. So we have lambda m minus 1. Our km is that we obtain 1 plus x squared over 1 plus t squared. Okay, and then x minus t, m minus 1 over m minus 1 factorial. Of course, this one is free of m. You can take out those, right? You can take out those. What else? This still we have m, so all right. Okay, so you have from there is 1 plus x squared over 1 plus t squared, that one, that, and then the rest, what you have, if m equal to 1, so you have 1 plus lambda x minus t 1 factorial plus lambda squared x minus t squared 2 factorial, and so on. Okay, this is the series for e lambda x minus t. So therefore you can write this thing, this is equal to 1 plus x squared over 1 plus t squared e lambda x minus t. So that's the resolvent kernel. So therefore the solution, therefore our solution to the non-homogeneous Volterra integral equation can be written as ux equal to fx plus lambda 0 to x rx t lambda ft dt. Once we obtain the kernel, the resolvent kernel, so we can solve this thing. So this is equal to, our fx is 1 plus x squared, then our lambda is 1, right? Yeah, lambda is 1, and then we integrate from 0 to x. Our r is given here, so we have 1 plus x squared 1 plus t squared e lambda x minus t, and we have ft. Our ft is 1 plus t squared then dt. Of course, from here you can solve this this equation. I think I just leave it to you. Yeah. So here t squared you can cancel out, not difficult. You can get it straight away. What left is 1 plus x squared, and then e to the x you can take it out, and lambda is 1. Okay, lambda is 1. You can put lambda is 1. Then x you can take it out. So basically you just have a 1 plus x squared plus this one, just give you 1 plus x squared 1 plus x squared. Here you can take it out, e to the e to the x. So what left is integrate 0 to x e minus t dt. So you can do this. So the answer is we have 1 plus x squared ex. So this is solution to the, so this is your ux, solution to the Volterra integral equation. Okay, so I have another example here to share with you. So let me give you one more example. if given ux is e to the x squared plus integrate 0 to x e x squared minus t squared ut dt. Okay, so another example here. For this equation, what we have, if we compare that with the general terms, we have fx is equal to e x squared. We have lambda equal to 1. We have k kernel. This is e x squared minus t squared. Then we use iterated kernel. Iterated kernel says what? We have k1 xt. Let me just keep on writing this thing so that we can memorize. Then this is equal to e x squared minus t squared. And then you can find km xt. This is integrate from t to x. Okay. K xz km minus 1 zt dz. So with this you can find what k2 is. Okay, you can find what k2. So k2 we have t to x, kxz, we change z with t, so e x squared minus z squared, and k1 is that zt, we change x with z, so e z squared minus t squared dz. Am I correct? Yeah, it seems okay. So if you do this, what we have, this is give you e x squared minus t squared, x minus t. Okay, then you can find k3. We can find k3 xt is integrate t to x. We have k xz, this is e x squared minus z squared, and then k2, yeah, k2z. So k2 is given as this, we change x with z, so we have e z squared minus t squared z minus t dz. If you solve this, so you can see basically from here you can see the pattern already. Yeah, from there you have z cancel out, so we have e x squared minus t squared. Okay, and then we integrate. That's all, I think. T to x z minus t dz. So not difficult to show this. Again, here you got, from there we have x squared minus t squared, x squared minus t squared, x minus t squared over 2 factorial. Yeah, and so on until you got the m terms. Km xt is given as e x squared minus t squared x minus t m minus 1 over m minus 1 factorial. Okay, so that's the m term of the kernel. Therefore, you can write the resolvent kernel. So the resolvent kernel is, from the general formula of the resolvent kernel, we have R x t lambda. This is summation of m1 to infinity. We have lambda m minus 1 km xt. So using this km that we obtained just now, so we have this is summation of m 1 to infinity. We have lambda m minus 1. Our km is e x squared minus t squared. Then we have x minus t m minus 1 over m minus 1 factorial. Okay, remember that our lambda is 1. Yeah, our lambda is 1. Remember that. Then you can rearrange this so that you can have a series form. From here, this is free of m. This is 1. This is 1. This is free of m. So I can take out that. So this gives you e x squared minus t squared. The rest just summation with that. So we have, when m is 1, so we have 1 plus, when m equal to 2, so x minus 1. When this is 1 factorial, then x minus 2 squared over 2 factorial, and so on. Okay, you can of course from there you can easily solve those. This you have e x squared minus t squared. This you have basically the series for e x minus t. This is t, sorry, this is t, this is t. Okay, x minus t. Okay, so therefore you can find the solution. Therefore the solution ux is given as, we have fx plus lambda 0 to x rx t lambda u ft dt. Okay, just substitute everything. Fx in this example is ex squared. Yeah, our lambda is 1. Then we integrate 0 to x. Our r is those ex squared minus t squared and ex minus t. And our fx is given here. So ft is e t squared dt. Okay, you just need to solve this. That cancel out, this cancel out with that, that you can put it there. So you have, this is e x squared plus this, we have e x squared minus x, and then integrate 0 to x e minus t dt. Okay, then here you can if you solve this, you can have, this is actually ex squared plus x. So this is the solution. So this is your ux. Okay, and then for the successive approximation, solving the volterra integral equation using successive approximation or iterated kernel that lead to the Newman solution, that I'll give in the next video. For this video, I give 3 examples. I think that's enough for this video. Okay, bye bye.